Hi guys, Dr. Musk back again. So let's continue our discussion of chapter 14, and now we're to section 14.9 where we talk about alkyl halides. So that's the name for the functional group where one of the carbons in our organic molecule is connected to a halogen, all right? And that halogen could be fluorine, chlorine, bromine, or iodine. We call them all alkyl halides, and they all tend to behave in similar ways. All right, so we do have to differentiate between types of halides the same way we differentiate between types of oxygens. All right, types of alcohols. And I don't know why the degree signs aren't showing up, but I'm going to draw them in. So a primary alkyl halide is where the carbon that has the bond to halogen also has a bond to only one other carbon atom. All right. A secondary halide has two bonds to carbon from that carbon that contains the halogen. And then finally, a tertiary halide has three bonds to carbon from that carbon that contains the halogen atom. All right, so we have to be able to classify those because as we get further into organic chemistry, you'll learn that different kinds of halides, they react different ways. So this is just a language thing. When we talk about a primary, secondary, or tertiary halide, you should know what I'm talking about. So let's talk about the physical properties of alkyl halides. Now, in a lot of ways, their physical properties are very similar to ethers. The reason why is, like ethers, they tend to be polar compounds because of the polarity of the carbon-halogen bond. The halogens are more electronegative than carbon, so we tend to have a net dipole on halides pointed toward the halogen atom. So the halogen side of that molecule will be slightly negative, and the other side of that molecule would be slightly positive. So because alkyl halides are polar, they have higher melting and boiling points than alkanes, which are nonpolar, but lower melting and boiling points than alcohols that have hydrogen bonding, the strongest kind of intermolecular forces, all right? Now, that being said, remember that this is just a statement that is true for molecules of similar sizes to one another. So, if we had a nonpolar alkane that was enormous, it might have a higher boiling point or melting point than if we had an alkane that was enormous, it might have a higher melting and boiling point than an alkyl halide that was much smaller. But if these are all the same size, then the stronger the intermolecular forces, the higher the melting and boiling point. All right, so let's take a look at some different alkyl halides and look at their boiling points and how they change with how big the halide is. So you can see that the other factor that influences melting and boiling points is how big the alkyl halide itself is. So a 2-carbon alkyl halide has a lower boiling point than a 3-carbon alkyl halide. And you can see also that when we have a 3-carbon alkyl halide with a larger halogen, a bromine instead of a chlorine, that makes the boiling point go up even more. All right, so the size of the molecule matters as well as the type of the intermolecular forces. All right, so stronger intermolecular forces is an indicator of a higher melting point and boiling point, but also larger molar mass, or in other words, the size of the molecule. That is also an indicator of higher melting point and boiling point. Both those things are true. All right. Now, alkyl halides aren't that polar. All right. So the polarity of the carbon-halogen bond is pretty small. Because of that, they're very, very different in terms of their polarity than something that's incredibly polar like water. So as a result of those being so different in polarity, alkyl halides are not soluble in water. All right, remember, like dissolves like. They're different enough from one another that alkyl halides just never dissolve in water. So naming alkyl halides is pretty easy. We've actually sort of been doing it a little bit already. All right. It's the same as naming all of the other molecules that we've named so far. We're going to find the largest parent chain in the molecule that contains the functional group, so in this case the halogen. There's our 7-carbon chain, so we know that's some kind of a heptane. We've got to give our halogen the lowest possible number because it's our functional group. So our halogen is at carbon number 2. We also have a methyl substituent group at carbon number 5. And then we name and number and alphabetize our substituents. So chloro comes before methyl. So this would be 2-chloro-5-methyl heptane. Pretty simple. So here are a few interesting alkyl halides. So chloromethane is a very, very low boiling compound, which means that on a warm day, it's probably a gas. On a really cold day, it could be a liquid. But it's produced by emissions from volcanoes in small amounts. That's interesting. Dichloromethane is a liquid at room temperature. It's also one of the most common solvents used in organic chemistry. It used to be used to decaffeinate coffee, and it is slightly toxic, so it's not used for that purpose anymore. Chloroform and carbon tetrachloride. So those are also very important organic solvents, but they're very toxic as well. All right, so particularly carbon tetrachloride is incredibly carcinogenic. And, 100 years ago, people used to wash their hands in this stuff when they were finished working on greasy motor parts for the day, that and chloroform both. So we've come a long way in determining things that are toxic, and people don't do that anymore with carbon tetrachloride because it's really, really bad for you. So let's move on to another kind of functional group, all right, the thiol. So thiols contain an SH group bound to a carbon, all right? They look very much like alcohols, but instead of an oxygen atom in between carbon and hydrogen, we have a sulfur. So sulfur is just below oxygen on the periodic table, and because of that, it reacts in similar ways. You can see that this could look just like an alcohol, other than the fact that there's a sulfur hiding in there instead of an oxygen. Four electron groups around that sulfur, which means that we're expecting a bond angle there of about 109.5, so a bent shape around that sulfur atom. Now, thiols don't have any oxygen-hydrogen bonds, all right? So in order for a molecule to contain hydrogen bonding, that type of intermolecular forces, there has to be a covalent bond between an oxygen and hydrogen, or a nitrogen and hydrogen, or a fluorine and hydrogen. So any of those kind of covalent bonds will allow a molecule to do that type of intermolecular forces called hydrogen bonding. So SH isn't any of those. So thiols can't hydrogen bond. As a result, thiols have proportionally lower melting and boiling points than similar alcohols. All right? So they are polar, but they're not capable of hydrogen bonding. Remember, that means that the type of intermolecular forces we would expect in between molecules of thiols are dipole-dipole forces, as opposed to the hydrogen bonding kind of intermolecular forces that we would expect with alcohols. So if we were naming thiols in the IUPAC system, the systematic naming, we'd name the parent hydrocarbon as a regular alkane, so like methane, propane, butane, whatever, and then add the suffix thiol. So if we have an SH group on a one carbon chain, that would be methane thiol. And if we had an SH group on the carbon number 1 of propane, it would be 1-propane thiol. So what if we had the SH group on carbon number 2 of the propane chain? Then we'd be talking about 2-propane thiol. So in both cases, the locant number locates where the thiol functional group is. All right, so that's pretty simple. We can name thiols just like we've been able to name all those other types of molecules in the IUPAC system by using the same rules. Importantly about thiols is they stink, all right? They are incredibly foul-smelling compounds. So skunk smell is a low molecular weight thiol. Another one that I like to reference often in the literature is there's a very small amount of a thiol, and it's normally butane thiol or propane thiol that is added to natural gas to give natural gas a foul odor. Humans can't detect the odor of natural gas, so what if you were filling your house because of a gas leak and you didn't know it? That's why natural gas coming from places that sell it is dosed with small amounts of thiols, and that way our noses can detect when there's going to be a gas leak. So using oxidizing agents, and there are a number of different oxidizing agents that could be used for this, we can oxidize thiols to disulfides. So how does that work? What happens is we end up taking two thiols and bonding them together using their sulfurs. So basically, we're breaking the sulfur hydrogen bonds and replacing it with a new sulfur-sulfur bond instead. Remember that breaking OH bonds and making carbon oxygen bonds is one way to do oxidation. So in this case, breaking sulfur hydrogen bonds and making sulfur-sulfur bonds is our way to do oxidation of thiols. So those thiols turn into disulfides. There are a number of different oxidizing agents that can make this happen. Pretty much any oxidizing agent you can think of. One that's commonly used in organic chemistry is iodine, I2. So note that the iodine doesn't show up anywhere in the product at all when that happens. In the end, what you end up with is a reduced form of iodine in the form of the iodide ion. So those iodines start out with a neutral charge, and they end up with a -1 charge. So they get more negative, while those sulfur atoms, in some sense, get more positive. There are lots of other oxidizing agents that will work for this purpose. So, for example, the chromium-based oxidizing agent that we were talking about earlier, K2Cr2O7, that would work just fine for this as well. There are a ton of oxidizing agents that will work for this purpose. Another one that's very common is just O2. So, for example, if we just leave a jar of a thiol open in air for long enough, a lot of it will self-oxidize to the disulfide. So any oxidizing agent that you can think of would probably work very well for this. And we can reduce disulfides back to thiols using a reducing agent. All right, and there are a number of those reducing agents that we could possibly use for this purpose, which is the one that I want to teach you guys about. I'll think about that. All right, so which reducing agent do I want to tell you guys about? We'll come back to that. All right, so I'll probably post a short video later on, and we'll do a couple of examples of the reactions from this chapter, and I'll pick a reducing agent that I want to teach you guys about. All right. So if you guys want to take a look here, all right, the reduction and oxidation of disulfide bonds is actually really important because it is the method through which perms are created. So hair has these disulfide bonds in it that allow the hair to maintain its structure and its either curly or straight shape. So if we treat the hair with a reducing agent, that relaxes the hair and takes a lot of its structure away. So what you can do is while the hair is relaxed, you can wrap it around curlers if you want to curl it, or you can keep it very, very straight if you want to straighten your hair, because you can straighten your hair with a perm as well. And then after that, the hair is treated with a mild oxidizing agent. So the oxidizing agent that is normally used in perms is hydrogen peroxide, H2O2, very common, gentle oxidizing agent that is used to reform disulfide bonds. But if you look, now that the hair is in curls, the disulfide bonds are different, all right? So we've added a different structure to the hair, one that maintains a sort of curly appearance instead of a straight appearance. And then after we rinse the excess peroxide out of the hair to prevent it from bleaching, then when you dry your hair up, your hair ends up being curly for a while. So that's pretty amazing, right? Who knew that reduction oxidation chemistry had something to do with how perms were created? But it certainly does. Well, it looks like that's the end of the chapter, so I suppose I probably need to pick a reducing agent for us to learn about in terms of reduction of disulfides, but one isn't coming to mind, and that's because there are like 100 of them that would work, and I can't remember which one I normally teach you guys off the top of my head, so I'll mention it someplace else. Other than that, thank you guys for paying attention.